では、定刻になりましたので、第13回目の計算科学技術特論 A を始めていきたいと思います。本日は理化学研究所の淳先生にParallelization of Molecular Dynamics という単位でご講義いただきます。メインは英語で、時々日本語を交えながらということでご講義いただきます。では、よろしくお願いします。
ご紹介ありがとうございます。できれば日本語で話してもいいんじゃないか思ったんですけど、やっぱりまだ日本語がよろしくないんで、英語で話します。でも皆さんいつでも質問とかあれば日本語で質問してもいいんで、よろしくお願いします。Today I talk about the parallelization of MD. First of all, I think it's better to describe the overview of MD. So in MD, we first evaluate energy and force. And from here, for every particle, we assign the parameter, which is named the force field. So using this force field, we first obtain the energy and force. And we change the equation of motion with integration style. So by evaluating force, we can update the momentum and coordinate. And from this one, we can obtain the long time and the trajectory. And this trajectory is used to understand the dynamics or some thermodynamic properties by generating ensemble. So to obtain the reliable thermodynamic quantities, long time and the trajectory is very important because that makes the good quality of ensemble. And I'll briefly explain the MD integration. There are several MD integration schemes, but here I'll talk about the Belashi-Bellet case. In Belashi-Bellet MD integration, first at time t, we evaluate force. And based on this force, we update our momentum from momentum at time t to time at t plus half delta t. After obtaining this momentum, using this momentum, we update the coordinates from coordinate at time t to t plus delta t. So here, delta t is a time step. And we obtain the new coordinate. And from the new coordinate, we evaluate the force at t plus delta t. And based on this, we again update momentum from momentum at t plus half delta t to momentum at t plus delta t. And again, update the momentum. And using this way, this one, we update the coordinate. And we evaluate the force. And we iterate these procedures over and over again. And using this way, we can obtain the trajectory of this coordinate or momentum. And this trajectory of coordinates can be used to obtain many statistical properties. So in MD, I said that we need to perform very long time MD simulation for good ensemble generation. But in MD, one time, in particular with all atom MD, one time step is very small. It's limited to 1 to 2 femtosecond because of atomic vibration of motion. So here, femtosecond is 10 to minus 15th power. It's a very short time. But on the other hand, many biologically meaningful events occur on the time scale of a millisecond or a microsecond. So if we consider millisecond time scale, then it means that we need to perform 10 to 12th power iteration. This is very challenging and difficult to work. So in this sense, we need to accelerate energy and force evaluation to obtain the long time MD trajectory. So this is the main time scale of each motion. So vibrational motion is on the time scale between femtosecond and picosecond. So we need to assign the time step based on this one, this small vibrational motion. But our many biologically meaningful events obtain this one. So if we want to obtain the Pauling phenomena, then as you see, we need to iterate many over and over steps. And this is the history of biological MD simulations. The first MD simulation is done in 1977 for PPTI protein. So in this case, they do not consider water molecules. So they just consider PPTI protein without water molecules, which consists of around 600 atoms. And even the time scale was just the picosecond level. But after that, the hardware and software are developed in many ways. And now we can simulate up to millisecond level for protein using very special MD machine like Anton and the recent Anton 3. This is one way. Then also, in the original MD simulation, the target system was very small. But using parallelization, we could even extend the target system size. And in our case, using K supercomputer, we could perform about 100 million atom system. And also, we could perform about 1 billion atom system. But in this case, the time scale was not so large. So we could perform short time scale. But somehow, using parallelization, we could perform the very large system. Another large system performed in another group was chromophore or SARS-CoV-2 virus. But still, we need to extend the simulation time scale and target system size for more realistic MD simulation. So in this sense, efficient parallelization is very important. So in all-atom MD, the potential energy consists of bond angle, dihedral angle, improper dihedral, and non-bonded interaction terms. Among them, these bond angle, dihedral, and improper dihedral, the computational cost is just order of n, where n is the total number of particles. So this one is not so much time consuming. But on the other hand, in the case of non-bonded interactions, which include van der Waals and electrostatic, because we need to consider all atom pair, the computational cost is order of n square. So this non-bonded interaction is the main bottleneck in MD simulation. And in fact, we usually do not evaluate this one in this way, but we are considering periodic boundary condition with infinite images. So let's consider some system consisting of these particles. In fact, our simulation is not this system, but making many periodic images of this system. And we calculate the energy and force based on this with many periodic images. So from this IJ particle index, we include the three-dimensional integer vector such that this one includes the periodic images. So for every particle, we consider the coordinate with the periodic image, and we calculate everything. So this one is very time consuming. So usually you do not calculate all of the things. First of all, in the case of van der Waals interaction, the energy is decayed very rapidly by increasing the interaction range. So if we increase the pairwise distance, then in some cases, you don't need to evaluate the van der Waals interaction. And in this sense, you can include some kind of threshold value. So for example, for this particle, basically you wanna calculate or you wanna consider all of the interactions between this particle and other particles. But in the case of van der Waals interaction, we can make this threshold value when you can consider only the interaction between this particle and other particles within this circle. Van der Waals interaction can be described in that way, but electrostatic interaction is much more difficult. Electrostatic, so in the case of van der Waals interaction, if you see this one, the energy style is just 12th power and 6th power of 1 over r. So it decays very rapidly. But if you see electrostatic, it's just 1 over r. So we need to consider very long range interaction. So we cannot consider such a threshold value easily. So in many cases, with electrostatic interaction, we decompose this one into real space and reciprocal space term. And in the case of real space term, by considering the complementary error function, we can consider the same threshold value as van der Waals. And reciprocal space interaction, here we make use of fast Fourier transformation. And the long range interaction in real space becomes the short range interaction in reciprocal space. So we can describe even the very long range interaction using this reciprocal space interaction term. So basically, the parallelization concept of MD is very simple. So it's true for every parallelization. So by just increasing the number of processors, we wanna accelerate the overall speed. For example, for this system, somehow by decomposing and by assigning the small amount of computational cost for each core, we wanna accelerate according to the number of processors. So in this sense, to obtain this kind of good parallel efficiency, we need small amount of computation in each processor. And each processor should calculate almost similar amount of computation. For example, this some processor has a very large of computation and other processor only have a very small amount of calculation and just idle. This is not good. So in this sense, we need to make a good load balance among processors. Also, among processors, the communication should be as small as possible. So to do this, I will briefly explain the parallelization. I think all of you might listen the parallelization, but so in this sense, I do not say very much in detail, but just I'll say very briefly. So one simple parallelization is using shared memory parallelization using OpenMP or pthread. So in this case, every processor shares the memory. And inside the loop, you can just use Plegma or OMP parallel, according in the case of C or Fortran. Because all processors share the data in memory, you don't need to modify the code so much. You can modify the code only a little bit using this thing. But here, for efficient parallelization or efficient shared memory parallelization, one of the most important is the memory access. So for example, this processor changes some value of memory. And this processor will use the value after this processor have evaluated something and write something in memory. And in this case, the order is very important. And also, concurrent memory access should be avoided. So in this sense, so memory access is one of the most important consideration in shared memory parallelization. And this is available for multiprocessor in a physical node. So nowadays, in our node, we have 1 or 2 CPUs, and each CPU has multiple cores. In this case, you can use this shared memory parallelization. In the case of distributed memory parallelization, in many cases, you use MPI. So in the case of MPI, we need to call some MPI-related module, like MPI init, MPI com length, MPI com size. And using this one, we assign the length number for each processor. And each processor has access only their own memory. And they do not touch the memory of other processor. So in this sense, we don't need to consider the memory access of other processors so much. But sometimes we need to understand the information of our processor result. So in this sense, we need communication using some sending and receiving data. And for efficient parallelization, the amount of communication data should be minimized. And in many cases, we use hybrid parallelization by combining MPI and OpenMP. So in this case, in the program, we just call MPI first at the very initial program execution. And for each computation, using this OMP parallel or programmer OMP, we make shared memory parallelization. So this is useful for minimizing communication costs with a very large number of processors. So as you know, nowadays, when you use a large number of nodes, and each node consists of some large or non-negligible number of cores, in this case, it might be better to do shared memory parallelization inside of a node and doing distributed memory parallelization using MPI for processors in different nodes. So many supercomputers like Fugaku, I think people wrote code using this kind of hybrid parallelization way. But there's another also consideration of parallelization. First of all, there's a low-level parallelization like SIMD is very important. So here, SIMD is named as a single instruction and multiple data. So, for example, let's consider this one. We have some array of A and B. We want to obtain the element of C by adding the element of A and B. So the first element of A and first element of B is added to and become the first element of C. So in this case, if we have 4 elements of A and 4 elements of B, and if we want to obtain the 4 elements of C, we need 4 addition. But in fact, by using SIMD, this A1, A2, A3, A4 can be considered as 1. And B1 from B1 to B2, B4 is considered also as 1. And this addition, we can just finish in one addition. So in this sense, because 4 additions is changed to 1 addition, we can accelerate the speed almost 4 times. So if you compile a program then if you see some vectorization message during compilation, then it means that you all in your program have also this SIMD parallelization. So, and this kind of thing is usually applicable to common task like graphic image or volume. And in most MD program, so this SIMD becomes one of the most important topics to increase the performance. But nowadays, many people move to also considering or even move to GPU. And in GPU, so we need to consider SIMD. So single instruction and multiple threads. This is similar to SIMD, but a little bit different from SIMD. So let's see for this example. Here, just consider we have how many threads? 1, 2, 3, 4, 5, 6. We have 8 threads. And let's consider this kind of conditional statement. If the thread index is less than 4, we perform A and B. And as we perform X and Y. Then how GPU will execute this one? Then according to each thread, so threads which the thread index is less than 4, they first perform A. And next, the other threads perform X. And next, the threads with the indices less than 4 perform B and Y and so on. So in this case, by making use of this condition statement, the computational time will be a little bit larger. But somehow, even in this case, inside of this one, this thread, we can parallelize using this SIMD instruction. So here, the important thing is that this instruction should be single. So many threads execute the same instruction at the same time. So in this sense, if you consider this kind of conditional statement, so the GPU perform in this order. But if you consider CPU with SIMD, it's in fact a little bit different from SIMD. If you consider single instruction, if you consider conditional statement like if sentence, then they do not perform in this way, but just perform in this way separately for everything. So there is some difference between this SIMD and SIMD. So yeah, this is a brief introduction of parallelization. And now I will explain the MPI parallelization of MD, in particular for non-boundary interaction in real space. So in fact, there are many parallelization ways. So I'll say just one by one from the easiest one to the more complicated one. The first easiest consideration of parallelization is to use replicated data approach. In this case, each process has a copy of all particle data. And you can just distribute or parallelize work by assigning each processor just a part of the whole work. So let's consider this one. Now there are two loops, do I and do J. So for each particle pair of I and J, you calculate energy and force. So in the case of this way, we can just make a MPI, can you define the MPI length as my length and total MPI number as PROC. By dividing this loop in this way, we can easily parallelize. So for example, here, let's consider there are 16 processes and the MPI length becomes from 0 to 15. So here my length, each processor has a value between 0 and 15. And the total number of processor is 16. And let's consider my length equals 0. Then they first, this one becomes 0. And they start I from 1. And they calculate all of j. So here, I and j calculation. First, they calculate all j with I equals 1. And the next, they jump to PROC, here 16. So the next one, next I index becomes 17. So they calculate between I equals 17 and all j. And the next one becomes 33. So the processor assigned as my length equals 0. They calculate of I equals, they calculate the I indices of 0, 17, and 32, and so on. Then how about the my length equals 1? Then they calculate, they start from 2. And they calculate the I indices of 2 and 18 and 34 and so on. So in this sense, they you can distribute all of the work using just changing this to loop. And finally, in fact, this energy value is not the completed one, just a partially added one. So we need reduction. You need to do reduction plus comment for energy and force. But in this case, so from this example, in fact, there are several problems. So for this one, let's consider. Here, j start from I plus 1. So if I is small, if I equals 1, then j start from 2. So the number of j is large. If I is large, then j becomes small. So in this sense, according to the atom indices, the computational cost is different. And as we increase the atom indices, because the computational cost is reduced, each processor might have different amount of computation. So here, I considered 4 MPI process. And in the case of MPI length 0, they calculate one indices of 1, I'm sorry, this 2, 3, 4, 5, and so on. And if you consider MPI length 3, it has much smaller amount of computation. So using this way, we cannot guarantee the perfect load balance. So here, MPI length 3 will finish all of the work much earlier than MPI length 0. And they are just to wait for the completion of MPI length 0. And also another problem of this approach is the large amount of reduction in communication. So I mean large amount of communication cost due to reduction. And this one, if you consider hybrid parallelization, like by combining MPI and OpenMP, this is also not so much difficult. For example, this is one example. Originally for MPI, we just divide this two loop by making a so length number and process number. But we can even combine, you can generate a new ID by combining length number and set number. So using this open OMP parallel, we can, each processor inside which MPI, we can obtain some kind of specific ID number, set ID number. And by combining our own length number and set number, we can obtain each ID number for each core processor. And we can just using this ID number and total number of processors as MPI processes times with total OpenMP process. Then you can parallelize also in this way. But here, we need to be very careful in OpenMP parallelization because energy and force, we need to sometimes energy is possible, energy is added by one processor, and this one can be added by another processor. So inside of OpenMP, we need reduction process. And after that, we need to again perform MPI reduction process. So, or even simple way is like this one. We do not use OpenMP set ID, but just we apply the OMP parallel do. Then we can just have the same, and inside of OpenMP, we can do OpenMP deduction. And you can, by applying the MPI deduction, you can obtain the same result. And first of all, this approach is the approach that you can first try because this is easy to implement. If we have some program, then you can easily apply this kind of parallelization approach. But in many cases, we do not recommend this kind of parallelization because the parallel efficiency is not good at all. There is no perfect load balance, and the amount of communication cost is not negligible. And in some cases, even parallelization might not be so useful. And it also needs a lot of memory because in this case, every process has a copy of all particle data. So this one cannot be used for very large system. So in many cases, people use domain decomposition parallelization scheme. So in this case, let's assume that this is the whole simulation space. And this simulation space is divided into subdomains according to MPI. So here, I assumed 9 MPI processor. And each MPI only consider the interaction of each local region, local space. And they do not care of the interaction of another region, another space. And we consider communication only among neighboring process. So this one need to have a communication with this one, and this one. And in this case, if you have a very large number of process, even though the number of process to be communicated is already fixed. Even for very large system, you don't need to consider the communication of all of the processor. You can consider communication only your neighboring processors. And in some cases, we need interaction between particles in different domains. For example, particles here and here. We calculate. Then, yeah, either the processor involved in this space calculate the interaction between this and this, or this processor may calculate it. But in either cases, we need communication. And the size of this communication size is dependent on some interaction range. Here we mentioned the cutoff values, which is the same as the threshold value of interaction range. And so by doing this one, even with the neighboring domains, we need to communicate for all of the data. We can communicate only for some specific region, small region of the whole space. And by increasing the number of processors, somehow we can reduce the size of this buffer region. And by increasing the number of processors, in this way, we can reduce the amount of communication. So this is a good thing of domain decomposition. Because each processor has only data over each regions of domain and additional buffer. They don't need the data over another region. So even for very, very large system, by just increasing the number of processors, it can reduce the data size of each processor. So in this way, we can apply for very large system simulation using large number of cores and using supercomputers like Fugaku. And almost MD software are making use of this kind of domain decomposition scheme. And also, each software has a different domain decomposition scheme, but yeah, almost they have similar kinds of domain decomposition scheme. And good thing is that it's easy to, it's not easy to implement, but if you can implement, then parallel efficiency is much better. And using this scheme, by increasing the number of processors, we can reduce the overall computational cost. And we can parallelize every part using this scheme. And even for very, very large system, by making use of large number of processors, we can somehow simulate. But we need to be very careful when we implement this scheme. And this domain decomposition scheme is highly dependent on the potential energy type and threshold value and so on. And just using this kind of domain decomposition, we can obtain the good performance for non-uniform particle distribution. Okay, so in the case of non-uniform distribution, in fact, people are considering several different approaches. One is tree method, where subdomain size is adjusted to have the same number of particles. So this one, regarding to this one, I'll explain later using our new CG coarse-grained MD simulation. And our scheme is Hilbert space filling curve, which map the multi-dimensional space to one-dimensional curve. And if they are very close in one-dimensional curve, then they becomes also very close in multi-dimensional space. And they parallelize in one-dimensional curve. Then it also parallelized in multi-dimensional space. Even though it's not a non-uniform distribution scheme, this scheme is also used in GPU parallelization. For example, if you see EMBER molecular dynamics software for efficient GPU parallelization, they make use of this Hilbert space filling curve. So if you just summarize the two different schemes of parallelization, the computational cost and communication and memory become like this. So by making use of domain decomposition, we can reduce even the communication by increasing the number of processes, and also it can reduce the memory size. And here, until now, I only explained the real space calculation of van der Waals and electrostatic. And reciprocal space, in fact, a little bit more complicated. So I will not say very much in detail, but I will just focus on the parallelization of fast Fourier transformation. Yeah. As I said in previous slide, electrostatic interaction energy can be decomposed into these three terms: real space calculation, and reciprocal space calculation, and safe energy term. Safe energy term is just constant. So you can just calculate once initially, and then you don't need calculate it again. So you can just remove in computational cost. Real space case, we made use of domain decomposition, as shown in the previous slides. And reciprocal space calculation, the energy is expressed in this way. And here, because of this Gaussian term, or in K vector, this term decays very rapidly. So we can somehow calculate this one without using so large a number of computational costs. And this term in fact is decomposed into this way. And here we need Fourier transformation of charge values. So in reciprocal space interaction, the most important is how to parallelize fast Fourier transformation. In reciprocal space calculation, the overall procedure is like this. We first have a charge in real space. And on grid, we put the charge to on grid using spline. And from this charge, we perform fast Fourier transformation. And from this value, with some prefactor, we calculate energy. And for this value, we perform inverse fast Fourier transformation. And finally, based on this value, we can calculate force. So in one MD step, in one reciprocal space calculation, we need one forward fast Fourier transformation and one inverse fast Fourier transformation. And in this FFT, the most important is the MPI all-to-all communication. So here I will briefly explain what is MPI all-to-all communication. Here you have a matrix with a two-dimensional matrix with A1, B1, C1, D1 to A4, B4, C4, D4. And just assume that processor 1 has the data of all A, and process 2 has all B data, and C has C, and 3 has C data, and processor 4 has D data. If you perform MPI all to all, then this processor 1 has the data of A1, B1, C1, D1. And process 2 has A2, B2, C2, D2, and so on. So if you compare this and this matrix, you can understand that MPI all to all is just same as the matrix transpose. And using this one, we can perform fast Fourier transformation. There are several parallelization of three-dimensional FFT. The first well-known is slab decomposition. So because the whole space is decomposed into slab-like one. So in this sense, in this case, each process is assigned a slab, this one or this one, over size of n times n over p. So if you consider this is x and y and g, x and y, they have all of the data, but in the g direction, they have only data over partially by divide the n in terms of processor p. And using this way, the scalability is limited by this graded number. And for perfect good parallelization, we prefer a situation where n should be divisible by the number of processes. So let's see. First, we perform the FFT in this direction. And this processor has a global data in this direction. We can just perform FFT in this direction. The second processor also perform FFT in this direction. And next, we want to perform FFT in this direction. In this case, because each processor has a global data over this direction, we need any communication. You can just perform FFT in this direction. And after finishing FFT, we want the FFT in this direction. But it's not possible because this processor has only a partial data of this in this direction. To perform FFT in this direction, each processor needs to know the data in this direction. So in this sense, we need to perform one MPI all to all. And you need to make the slab like this shape. And after making this shape, we can perform FFT in this direction. So in this case, we need only one communication or one global transpose. So this one can be very fast if we use small number of processes. But the number of processes available is limited. You cannot use very large number of processes. And to overcome the parallel problem of slab decomposition, in MD, also many people consider two-dimensional decomposition. This is also named as pencil decomposition because the shape of each processor has a pencil shape. So first of all, each processor has a data of this pencil shape one, and they perform FFT in this direction. And next, we want to perform FFT in this direction. In this case, we need a communication. So to do this, processors with the same color here, process of this one, this one, this one have a communication to each other. And the processors with blue color also have a communication. And the purple ones also communication among them. And you can make a shape like this one. And you can perform FFT. And to perform FFT in this direction, we need to perform MPI auto communication. So in this sense, we need two communication, but the number of processors involved in the communication is not so high. So here, even though we consider 9 processors, we can consider communication only among 3 processes. So this one, we need communication twice. And the overall FFT step is 5. But the number of processors involved in the communication will be smaller than slab decomposition case. So if you use very small number of processes, then this one will be slower than slab decomposition. But we can increase the parallelization when we use larger number of processes. And in our group, I also consider 3-dimensional decomposition. So in this case, each process has a data of each cube, small cube. And using 1-dimensional MPI among these 4 processes, we can make a shape like this way. And you can perform FFT in this direction. And among these 4 processes, we have a auto communication again, and we make a shape like this way. And to perform FFT in this direction, we perform MPI auto among these 4 processes. And we can make this way and perform FFT in this way. So this one requires more communication than existing FFT. But good thing is that the number of processes involved in the communication is small. So this one will not be useful when you consider very large, when you consider small number of processes. But if you consider very large number of processes for very large system, this one can be very useful. So based on so this is a parallelization scheme used in FFT, and based on this, I'll talk about some case as a case study. I'll talk about the parallelization of a Genesis MD on the Fugaku supercomputer. And MD software Genesis has been developed in the CAN, and it allows high performance MD on parallel supercomputers like Fugaku, Lumi, and so on. And it's free software on the LGPL license. So if you are interested, please download. You can just access this website, and you can understand many information about this MD software. And we are making use of domain decomposition. And also in Genesis, we also have a simple parallelization scheme using the replicated data method. And I do not say in detail, but you can, one thing I can say is that the whole space is divided into subspace according to the number of MPI. And this space is again, we parallelized by OpenMP. And somehow even this space, we make some unit domain space named cell. And this cell is used for every particle interaction. And for every particle data, if we follow the global atom indices, then particle data is saved in memory in this way. But we reorder the particle indices such that the particle in the same cell are grouped together. So in this sense, we can somehow increase the accessibility to memory. And this is too much technical, but just the one thing I can say is that for a particle in this cell and in this cell, where this interaction is performed, it's considered by the midpoint of these two cells. So in fact, this data of A is in this MPI, and other data B is in another MPI. And this interaction, where we calculate interaction, is based on the midpoint, where the midpoint cell is. The midpoint cell is here. So the processor related to this subdomain will calculate the interaction between particles in cell A and particles in cell B. In some cases, midpoint is not defined uniquely. Then we decided based on the load balance. And so in fact, this is what it did in Genesis. For all MD simulation space, we make a unit domain named cell according to the threshold value. And then we assign the same number of cells according to MPI. And for each data in this MPI, we communicate with the neighboring domains only for the neighboring cell in this direction. And for upper region, we communicate with the upper regions or with this one. And each MPI has the data of its own subspace and additional upper region. And we can calculate. And for this one, we make a cell pair index. Instead of atom pair, we make a cell pair index. And if cell pair is the midpoint cell is inside of this domain or not. If yes, then we parallelize by OpenMP. This is the overall hybrid parallelization process in Genesis. And we changed the parallelization scheme a little bit on Fugaku, but it's too much technical, so I will not say so much. And in the case of this Fugaku space interaction, even though the parallelization of FFT is important, but also this part is also important. How to make the charge from real space to charge on grid data. Basically, the charge in real space is some partial charges is assigned to on each grid, on top of each grid. And this partial charges on grid is used for this Fugaku space calculation. So to do this, because this charge on this space is spread to the grids nearby. In fact, now we have charges of this domain and buffer region. And the generated charge on grid will be like this. And among them, we only select the charge grid of this region. And next, we perform FFT. This is the previous Genesis scheme, but this one has several problems. And so now we change the scheme a little bit. So we don't consider this buffer region. We only consider charges on this subdomain region, and we generate the charge grid on maybe in this space. And then from this one, we perform communication. First of all, to the neighboring, we communicate this charge grid data we send and receive to the upper and lower. And the N each subdomain has a charged grid data with this way, and they send this charged grid data to left and right. And finally, each subdomain has a final charged grid data which can be used in FFT. But this is too much specific, so I think you don't need to worry about so much about the understanding of this one. And anyway, using this way of parallelization on Fugaku, we could obtain the good parallelization scheme, good parallel efficiency. So for this system, 100 million atom system, here using 4,000 nodes, we obtain 4 times better performance than Genesis on K. So by using just 1/8 number of nodes. And for very, very large system like 1 billion, we obtain this performance. And we believe that this one is one of the best performance for 1 billion atom system. And here, briefly, I'll also say about the non-uniform particle distribution case. So until now, I only explained the all atom case. In this case, I include all of the water molecules. But in many cases, people want to perform larger scale simulation and want to understand very macro scale behavior. But in fact, this one is not so easy. So until now, people consider about 20,000 CG particles or very large system with ultra scale, ultra coarse grained particles. But to obtain many meaningful results, we don't need to assign very ultra scale CG. You need to keep some CG level, but you need to increase the system size much more. So here, if you see this one, many people consider this slab-like scheme by considering only the large dimension in Z direction, but very small in XY direction. But for very meaningful result, we need to perform the MD like this way. But in this case, we need to consider 100 times larger system size. And in this case, in this coarse-grained MD simulation, the main problem is that we do not consider water molecules, and the density is not uniform at all. In the case of all atom MD, every space there's atoms, and density is almost uniform because they are water molecules. But in coarse-grained level MD simulation, or if we do not consider solvent molecules, for some part they have a very high density, but in some part there is no density. And in this non-uniform distribution, you need to consider load balance very carefully. So this is our new parallelization scheme for load balance. So the idea is like this. This one is the whole system. And we make a unit domain named cell as all atom case. And first, we make a boundary such that left and right has almost a similar number of particles. And then each region, for this region, we make a boundary such that upper and lower has a similar number of particles. And this one is also. And we iterate this procedure over and over again. Then, finally, the number of this partition will be same as the MPI number. And the number of particles in each subdomain will be similar to each other. So for coarse-grained MD simulation, we implement this scheme into CGLine engine in Genesis software. So if you are interested, you can search for this paper. And of course, in many simulation cases, during MD simulation, the density can be changed like this way. And we can also change the domain size according. So in this case, in this way, during MD simulation, you can keep the load balance. And using this way, you can obtain much better parallel performance. Here, let's consider these two systems. Two systems has the same number of particles, but the volumes are different. And because the number of particles is the same, the performance also should be similar to each other. And if we see the performance on Fugaku, here 89 is the simple parallelization scheme using the replicated method. And here SP9 like is this uniform domain size, domain decomposition with same domain size. And our CG9 here, we assign a different domain size to obtain the similar number of particles in each domain. Then, using this domain decomposition scheme, we can have a much better performance than the simple parallelization scheme. And by using this way, from this to this, we can even obtain much better performance result. And if we apply this way, these two systems we obtain different performance result. But by properly making use of this way, we have these two systems, we have a similar performance result. And yeah, so using this way, we could obtain some biological condensation phenomena of this one. So each point is just one protein chain. So this is very large system. And this protein chain, we using efficient parallelization on Fugaku, we could obtain this condensation phenomena. This one, yeah, I'll show you. Oh, this does not work. Yeah. So in fact, without using good parallel efficiency, we couldn't perform this kind of MD simulation. But by considering efficient parallelization, in fact, we could perform this large-scale MD simulation, even with non-uniform particle density. And yeah, you have still time. Also, in MD, you should consider parallelization using GPU. And I think GLOMAX is one of the very popular MD software using GPU. And I will briefly explain the GPU parallelization by GLOMAX. So I said that in GPU case, SIMT, SIMT is very important to parallelize. And in this, usually in GPU, warp size is 32 for NVIDIA's one, and AMD's one has 64 wavefront. So in this sense, 62 different data should be calculated at once using the same instruction. To do this, in GLOMAX, they make a cluster of each particle. So they consider some kind of group-group interaction for particle-particle interaction. And each group interaction, the number of particle interaction becomes 32 in NVIDIA, GPU, and 64 for AMD GPU case. By making this kind of group size, just using the single instruction, they can very efficiently make use of GPU, and they can obtain the good performance result. And also, in many cases, CPU-GPU heterogeneous offloading is important. So in GLOMAX, they consider several different offloading schemes. So for example, one simple thing is calculate everything on CPU. And another option is calculate the CPU for labor search and bonded and PME in reciprocal space interaction and so on, and only assign GPU for non-bonded interaction, real space interaction. Also, they can change different options. If they have multiple GPUs, then one GPU is assigned for real space interaction, and other GPU is assigned for reciprocal space interaction. And in some cases, they can even include other forces, other bonded interaction into GPU. So in this sense, by making use of different hardware architecture, you can use different CPU-GPU heterogeneous offloading. In the case of Genesis, to make use of SIMT, so for each particle in different cell, particle pairs, we make some kind of block of 8x4 block of particle pairs. And in the case of NVIDIA GPU, because the warp size is 32, this particle pairs is considered as one block, and we apply the SIMT, single instruction multiple set, for GPU parallelization. And also, for recent AMD GPU on the supercomputer, we also consider different combination of a block. How to make a block size like 8x4, 4x16, and so on. And we obtain the best combination of the block size also. And in fact, from this one, we found that the assignment of block size is very important to obtain the good parallel performance on GPU. So, for example, here, if you see, this one is the AMD GPU case. And AMD GPU case, if we apply the block of 32 by making a block of 8x4, the performance is like this. But if we change it to block size of 64 as 4x16, it is the total time is reduced. And again, if we change this block combination as from 4x16 to 8x8, which again are reduced. In some cases, even we use the 64, if the decomposition is like 32 times 2, the performance is not so good. We need more computation time. So recently, we found that on AMD GPU case, this one or this one is the best scheme. So if I say it again, for example, if you consider interaction between different cells, like this cell and this cell, we make an index of this cell here, and we make an index of this cell here. And for every particle pair, we, according to this combination, it can make a different block. It can make a different block. So this one is, for example, the block of 16 times 4, and this is a block of 32 times 2. You can say that this is one block. And if you see this one block, some threads works, but there are many threads just idle here. Then the parallel efficiency is not so good. But if you make 16 times 4, then inside of this block, every thread calculated. Inside of this block, also. But in this case, in this block, some does not calculate. So in this sense, still, Genesis GPU parallelization is not perfect. But somehow, by efficiently controlling the number of size in each block, we can avoid this kind of situation where many threads are just idle and waiting for another thread. And also, Genesis, we have a CPU-GPU offloading, and where GPU calculates only the real space number injection, and other parts are done on CPU. So our main concept is to use GPU for computationally intensive part and assign GPU for computationally intensive part. But nowadays, because GPU is very fast, much faster than CPU, and I think we also need to consider multiple heterogeneous CPU-GPU offloading like Glomax case. And now we are doing development for multiple heterogeneous offloading option in Genesis. Yeah, this is the summary. Basically, we can consider parallelization of MPI and OpenMP. MPI is mainly used for discrete memory parallelization, and OpenMP is used for shared memory parallelization. And you can consider hybrid parallelization by combining MP and OpenMP. But nowadays also, we are considering GPU for much high performance calculation, because in GPU there are many number of threads, and by efficiently doing parallelization using SIMT, we can obtain much better performance than CPU only case. And here I do not say so much about the GPU, but in GPU case, how to make use of memory is very important. Also, there's a hierarchy of memory on CPU and GPU. And on GPU case, how to make use of constant memory or shared memory or or global memory. Depending on the memory uses, the parallel efficiency or overall performance can be very different to each other. And here we mention about the parallelization of MD, mainly by domain decomposition in the parallelization of non-bonded interaction. And please keep in mind that it's also true in other parallelization scheme. In parallelization, important is to minimize communication cost and maximize the parallel efficiency. And also, hardware-aware optimization is important. Your approach of parallelization for CPU and GPU can be very different to each other. Yeah, that's all. Thank you for your attention.
Thank you very much. どうもありがとうございました。
ありがとうございます。